Today we will learn three-dimensional graphics. In case of two-dimensional transformation, the matrices in homogeneous coordinates are 3 into 3 matrices. We just increase one dimension, 2 becomes 3, so the matrices are 3 into 3. So in case of 3 dimension, it becomes 4 into 4 after increasing one dimension. So as in 2D, a standard representation of a point x, y, z, w with w not equals to 0 is given by x by w, y by w, z by w and 1. So what is translation matrix for 3D? If a point P in 3 dimension, after translation, the new position is P dash, it is x dash, y dash, z dash and the translation distances are tx, ty, tz, then we get this translation equation. Now the matrix representation of these three equations are this. So when we multiply first row with first column, we get first equation, and second row with this column we get second equation, and third row with this column we get third equation. So this is the translation matrix for 3D. In case of 3D, the scaling matrix is this: x into sx, y into sy, z into sz. So this is the scaling matrix for 3D. In case of rotation, we know rotation matrix for 2D is x dash equal to x cos theta minus y sin theta, y dash equal to x sin theta plus y cos theta. But if it becomes 3D, then we can say how many planes are there: xy plane, yz plane and zx plane. So in case of xy plane, z axis are same. So we can write z dash equal to z. For getting the rotation in other plane, you have to use cyclic permutation, means just replace z value by y value, replace y value by x value, replace x value by z value. Means see here, replace x value by y value, replace x value by y value, replace y value by z value, y value by z value, x value by y value, so y value by z value, so z value, and z value by cyclic, because it is cyclic, by x value, so x value. In this way we get second three sets of equation. Here x coordinate is same, and for after rotation the x coordinate is same, and the last set are z dash equal to replace y value by z value, y value by z value, z value by x value, z value by x value. In this way we get the last set. So here y coordinate are same before and after rotation. So we get three sets of rotation matrix. So we get three sets of rotation matrix. So from the first set of equation we get this set of rotation this matrix. From the second set of equation we get this matrix, and for the third set of equation we get this matrix. When we multiply this row with this column, we get the first equation in this way. Now 3D shearing. 3D shearing, in case of 3D shearing transformation, can be used to modify object shape. So we know the shearing for 2D, it is parallel to x-axis shearing, it is the matrix for parallel to y-axis shearing. So in case of 3D, if we represent a matrix, an example of a 3D shearing, the following transformation matrix produces when it is parallel to z-axis shear. So in case of z-axis shear, see, with compare with this, in case of z-axis shear, see here, it is in case of x-axis shear it is this, in case of 2D it is, in case of 3D. So in case of z-axis shear it is 1 0 a0 1 0 1 b0 0 0 1 0 0 0 0 1. The effect of this transformation matrix is to alter x and y coordinate values by an amount that is proportional to the z value while leaving the z coordinate unchanged. Now your task is to define shearing matrices for x-axis and y-axis shear, but in case of 3D. That's all for today. Thank you.